So far we have seen two operations that are push and pop operations. Push operation basically added the new value at the tail end of the singly linked list, and pop operation basically deleted the value from the end of the singly linked list. That is, basically we have deleted the very last node, right? So by implementing these two operations, basically we have performed the addition and removal operation on a singly linked list at the end of the singly linked list. What if we have to perform the similar operations on the beginning of the singly linked list? That is, if I have to add a new value at the beginning of the singly linked list, or if I have to remove the value from the beginning of the singly linked list. Now let's get on to implementing such functionalities. So the functionality which basically adds new value in front of the singly linked list is basically nothing but a unshift operation. So as part of unshift operation, what we will exactly do is we will take the value from the user and we will basically create the node object with the value that user has given, and we will make sure that this node is getting added at the beginning of the singly linked list. Okay, just remember that unshift operation is used for adding the value in front of the singly linked list. So we already have head node and tail node and length inside our singly linked list representation, right? Since we are adding the new value in front of the existing head node, whatever the new node that we are adding will get added here. Okay, so we have to make sure that whatever the remaining singly linked list is available already, we have to make sure that we are keeping the track of the next pointer of the existing head node inside the new node that we are adding. Okay, so that is a simple shift operation. That means we will basically add the new value in front of the existing head node of a singly linked list. So what all are the different cases that can come while performing the unshift operation, right? Obviously the first case is when the singly linked list is empty. When the singly linked list is empty, right, whatever the head comma tail that we are maintaining, they both will be equal to null or none based on our programming choice of implementation, and we are maintaining none in head and tail if we are choosing a Python based implementation, right? So since I'm making this course as a programming language agnostic course, so I'm trying to explain it for all the languages here. And inside the length we are having 0. Now whatever the node that we are adding, right, since the singly linked list is empty, whatever the new node with the value that user has passed, let's say 10 here, that will become the head node and tail node, right, and length will become 1. So since the singly linked list is empty, we know how can we check a singly linked list is empty, right? Using that logic, we will obviously check the singly linked list is empty or not. If it is empty, we will update the head and tail with the new node that is getting created with the value that user has passed, and we have to make sure that the references are getting updated properly as well. In the end, we will increment the length by 1. Now let's try to handle the second scenario where the singly linked list is non-empty. That means that we have certain number of nodes available inside the singly linked list. Now our aim is to add the new node in front of the singly linked list. That means we will have to add the new node in front of the head node that we are maintaining. Let's assume that in that case the singly linked list has some, let's say 3-4 nodes available inside the singly linked list, right? And we have the head node and we have the tail node. Let's say 10 code and true are the values that are present inside the singly linked. Now let's assume that user has given one string by the name, let's say false. Okay, now our aim is to insert this false or perform unshift operation using that false in front of the existing head node. That means false, we will create the object, right? So we will create the node object, and inside the false node we have to have the next, right? And that next we will update it with the existing head node of the singly linked list. In that way we are not losing the remaining singly linked list that we already have. So we have to make sure that the next of the newly added node is getting updated with the reference of the head node. Okay, because head node is the next node of the false, because we are adding a new node in front of the singly linked list. And if you observe here, right, whatever the head node 10 that we had earlier, this will no longer be the head node of the singly linked list. So the head node will be the newly added node on a singly linked list. So we have to update the head to the newly added node on a singly linked list. And we also have to make sure that the length also getting incremented by 1. Okay, we have to increment the length by 1, because after all we are introducing a new value into the singly linked list. Okay, these are the two scenarios that can come when we are performing the unshift operation. Okay, when we tried performing the push operation, we tried adjusting the tail end because we are adding the new value at the tail end of the single linked list. Now we are trying to perform the new node addition operation in front of the head node. So we have to make sure that the necessary changes are being tracked inside the head node and tail node and length appropriately according to the case that we have discussed. Okay, so that is how we perform the unshift operation. Now we have seen the different cases that could arise when we are performing the unshift operation, right? According to that, let's write the pseudo code for the unshift operation. So what exactly we will do here? Here we will basically take the or write the function called unshift function, and it will basically take the value that user wants to add in front of the head node of the single linked list. As part of this implementation, first what exactly we will do is we will create the object of node with value that user has passed. Okay, so we will assign it to some variable. I mean, you will exactly see how we are storing it in some variable in the implementation, right? So, since this is a pseudocode, let's just try to put our algorithm into terms. And after creating the object, first what exactly we will do? We will check if the singly linked list is empty. If the singly linked list is empty, so what exactly we will do? Whatever the node that we are adding will be the only node that will be there inside the singly linked list. That's why we will update the head with the new node that we have created with the value that user has passed. And since that is the only node, tail node will also be pointing to the same node object that we have created. And length we will increment by 1, length plus 1. In the end, we will simply return the new node object. Okay, because that is the node that we are adding. Otherwise, what you can do is you can also return the head node which contains the new node that we have added as well. Okay, so this is the pseudocode where we are trying to handle the case where we don't have any nodes inside the single linked list when we are trying to perform the unshift operation. Similarly, let's just write the otherwise case. That means that single linked list is not empty. So if the single linked list is not empty, what exactly we will do is first we will read the head node. Okay, just read it into some variable because we have to use that node as a next reference in the new node that we are adding. So update next of new node that we created with head node that we read. So inside the node that we have created with the value, we have updated the next reference. That means that the connection has been established with the remaining singly linked list. And if you observe the logic that we discussed earlier, right? So whatever the node that we are adding will become the new head of the singly linked list. That's why we have to update the head equal to the new node that we are adding. In the end, we have to increment length by 1. Okay, so that is how before closing this, we have to return the new node that we have added. Otherwise, since the head node will contain the, whatever the head node that we are maintaining inside the single linked list will contain the new node that we are adding, right? Because we are making sure that, since we are adding the new value in front of the head node, we have already updated the head node. We can return head node as well instead of returning the new node object. Okay, it is up to your choice. Now let's quickly implement the unshift operation according to the steps that we have discussed previously. So inside the single linked list implementation that we are doing, let me just add the function which will basically add the new value in front of the existing head node. That's why we call this function as unshift, and let's just name the function as unshift, and it will basically take the value of type t that we define in the while initializing the singly linked list class. Now obviously, like I've explained in the push operation implementation, whenever we are introducing a new value, we have two scenarios. One is empty singly linked list and non-empty singly linked list. We need to write the logic for honoring both these scenarios. But the important thing that we have to remember here is, as part of the unshift operation, we already have the head node of the singly linked list, right? Before that head node, we need to add the new node with whatever the value that user has passed. As a result, we need to update the newly added node as a head of the singly linked list, because as we are adding it in front of the head node of the singly linked list, it is becoming the very first value on the singly linked list. But anyway, if the singly linked list is empty or not empty, in both the scenarios, we will be needing the object of the node that we need to introduce with whatever the value that user has passed, right? That's the reason why let me just create the object of node with whatever the value that user has passed. Okay, now to check if the singly linked list is empty, let me just rely on the length of the singly linked list. If the length of the singly linked list is 0, then obviously whatever the node that we want to introduce, that will be the only node in the singly linked list. As a result, it is the head node and tail node as well on the singly linked list. So here in this case, we will update the head to the new node object that we have created, and similarly let me just update the tail also to the new node that we have created. Anyway, along with this, we also need to increment the length by 1, because we are adding one value into the singly linked list. In the end, we need to return the new node that we have added. So we can simply return new node object here. Okay, so we have successfully handled the case where we want to add the value on a empty singly linked list as part of the unshift operation. Now obviously in the second case is, whatever the singly linked list in which we are trying to add the new value in front of the singly linked list, it might not be empty, right? That means we already have the head node in the head variable that we are keeping track of, and we have the new node as well. Now as we are adding the node in front of the existing head node, the newly created nodes next will be whatever the head node that we already have. That's the reason why first what we will do is, we will simply update whatever the new node that we have created dot next, we will assign with the head node of the singly linked list that we have right now. So we have properly adjusted the next connection so that the entire singly linked list can be traversed. Basically there are no abnormalities and no links have been broken in the singly linked list by adjusting this next. Now as we have added the new node in front of the existing head node, this node will be the head node of the modified singly linked list. So let me just do this dot head is equal to new node. Okay, as we have added one value into the singly linked list, the length should be incremented by 1. In the end, we can simply return whatever the new node that we are adding here. Okay, so that is something that we need to remember. So we have successfully implemented the unshift operation here, and if you see here, these two lines of code is common in both the cases, right? So we can simply copy paste that logic here as well. So we can simply remove that also here, so that it will be perfectly fine. If you want to move this dot head also to here, that is also absolutely fine. It is up to you, because those changes are common in both if condition and else condition. That means if the singly linked list is empty and non-empty. Anyway, so that is the unshift operation, which basically adds the new value in front of the existing head node of the singly linked list. Now what we can do is, let me just comment out all these pop operations, and let me keep this traverse so that we will be able to see before adding the value and after adding the value. In the beginning, let's just assume that there are no values at all in the singly linked list. So we haven't pushed any value into the singly linked list, it is empty. As a result, the traverse operation should basically print the empty line. After that, let's just try to add SLL dot unshift of, let's just say I want to add value 20 into the singly linked list. So if I execute this now, as part of the unshift operation, since the singly linked list is empty, whatever the node that we are adding will become the head and tail, and length will be incremented by 1, and the new node will be returned. So if I execute this as part of the traverse, we should see only 20 on the console. So see, as part of the first traverse, we've got the empty line. As part of the second traverse, we've got 20. So this basically validates the first scenario when we are trying to add the new value, perform the unshift operation on an empty singly linked list. So the logic went into this if condition. Now let's try to check the scenario where we have some values in the singly linked list. Let's just assume we have, before performing the unshift operation, we have performed the push calls. As a result, we already have the 3 values, and in this the first value is 0, right? As part of the unshift, we need to add the value before 0. So in the modified singly linked list traverse call, we should basically see 20, 0, 10 and -10. So if I execute this, that's the output that we should see on the console. Let's just see the same thing. See, that is what we have gotten. As part of this traverse call, whatever the values we had, we've got that as part of the first print here. And if you see the second traverse here, after adding 20 before 0, this is the modified singly linked list. In this, 20 is the first value, right? That means if at all, if you want to print the head and tail also, that is absolutely fine. You can print and confirm that head is 20 and the tail is -10. Okay, so that is how we implement and validate the unshift operation on a singly linked list, where we will add the value in front of the existing head node of the singly linked list. Now that we have implemented the unshift operation on a singly linked list, let's try to analyze the space complexity and time complexity involved in this unshift operation. So obviously, let's just try to talk both of them in terms of best case as well as worst case. So obviously, in performing the unshift operation, there will not be best case or worst case. Usually people will think that when there are no values at all inside the singly linked list, there will be best case, and the worst case is obviously when we have n number of nodes inside the singly linked list, right? So in both the cases where the singly linked list was empty, if it is empty, we have updated the head node and tail node with the new node that we have created with the value, and these are simple assignment operations, right? In that case, obviously simple assignment operations will take constant amount of time. As a result, in the best case scenario, the time complexity is order of 1. Similarly, if we have n number of nodes as well inside the singly linked list, what exactly we did? We simply created the new node object. Okay, previously we had head this and we had tail here, and we simply created the new node, and we simply updated the next of newly created node with the existing head node. So that is also a simple read and assignment operation, right? So we know those operations will take constant of amount of time only. As a result, and even if you have n number of nodes on which you are trying to perform the unshift operation as well, the time complexity will still remain order of 1 only even in the worst case scenario. Okay, so there is nothing like worst case or best case, both, all of them are best cases only in the way we are implementing the unshift operation. Now let's talk about the space complexity. Obviously, when we had no values inside the single linked list, we are updating the head and tail and we are incrementing the length by 1. So those operations are simple assignment operations, right? As a result, the space complexity will also remain inside the best case scenario. When we have worst case scenario also, we can directly read the head node, because inside the single linked list representation that we are doing, we have the head node, tail node, and we have the length as well. So all we have to do is we have to read that head and we have to assign it to the next of the newly created node. So obviously these read operations will take only constant amount of memory, and in the end we are updating newly added node as a new head of the single linked list, right? As a result, that operation will also take constant amount of memory. As a result, overall space complexity will be constant, that is order of 1 only, even in the worst case scenario. Okay, so that is how we exactly perform the or calculate the time and space complexities involved on a unshift operation.